Hi, this is David Heubner from the Warren Ponds campus, and this is SIT399 assignment 2. This is the question I chose to do, the two-variable LP problem of your own, and plot it, solve it, and explain sensitivity analysis, objective binding constraints and non-binding constraints, and the meaning of shadow price. So here's my problem. Microfruit is a big computer manufacturer that produces both laptops and desktop computers. For each sale, a laptop makes $100 profit, and desktop computer makes $250 profit. In the factory, the Microfruit company has a maximum of 2,000 production materials per day. Each laptop uses 15 units of material to produce, and the desktop computer uses 40. Microfruit has an expected demand of at least 50 laptops and 25 desktops sold per day. Microfruit want to maximize profit while satisfying the demand and production constraints. So letting x1 equal the number of laptops and let x2 equal the number of desktop computers produced each day. This is our objective function here. Here is our production constraint, and here are two demand constraints, and of course the non-zero constraint. So here are our constraints. Here's the production one here. This is the two demand ones. We can see here that if we sub in a 0 into both sides here, it will satisfy this statement. So therefore it will be this side of the line. And obviously for x1 greater than 50, the values will be over here. And for x2 greater than 20, these values up here. So therefore this will be our objective region, optimal region rather. And our optimal solution will be right here in the intersection between x2 is greater than 20 and the production constraint. So finding the optimal solution, we saw before that the optimal solution lay in the intersection between the production constraint and the desktop computer constraint. So by using simultaneous equations, we can solve for our x1 and x2 values here and here. And therefore our optimal solution is x1 equal to 80 and x2 is equal to 20. And our optimal z value turns out to be $13,000 per day. Sensitivity analysis is the study of how changes in the cost of an LP can affect the optimal solution. In other words, determining the range of values that we can alter in the objective function without changing the optimal solution. So as we can see here, the gradient for this one is undefined as it's straight vertical, and this one here is horizontal, so it's 0, and the production constraint here is negative 0.375. So introducing a new arbitrary variable c1 here in place of the 100 in front of the x1, we can actually rephrase the objective function as a y equals mx plus c type formula. So as we had before, see this was supposed to be x2 and x1. So y, and here's our m, and here's our c. So we got m equals to negative c1 over 250. Comparing with the other gradients, we had 0 and we have negative 0.375. So comparing with the other gradients, we can see that negative c1 over 250 is going to be greater than negative 0.375, but less than 0. Timesing both sides by negative 1 on 250. The signs flip, and C1 will be less than 93.985 and greater than 0, or approximately 94 as well. So therefore, to keep the same optimal solution, C1 must be between 0 and approximately 94. So doing the same thing for the coefficient in front of x2, we'll put a C2 in place of the 250, and we'll do the same thing, taking this 100 over to this side, making it negative, having C2 times x2 on this side, dividing both sides by x2, and then having x2 on its own. Therefore we can get the same statement as before, y equals mx plus c, with our gradient being negative 100 over c2. So same as before, comparing with the other gradients. See here, negative 0.375 is less than negative 100 over c2, and then timesing by negative 1 over timesing by negative c2, sorry, then the signs flip, get the c2 on the top, divide both sides by 0.375, therefore we can see c2 is greater than approximately 266. And on the other side, similar thing, and It's a 0, so you can't really do much with 0, but still flip the sign, and we can see that to keep the same optimal solution, C2 has got to be between 0 and approximately 266. The binding and non-binding constraints. A constraint is binding if the left and right sides are equal when the values of the optimal solution are substituted in. Conversely, a constraint is non-binding if the left and right sides do not equal when the value of the optimal solution is substituted in. So if you put our objective function and constraints back in, here's our optimal solution. Substituting it into the first constraint, you get 2000 equal to 2000, so therefore it is binding. Constraint 2, x1 is greater than or equal to 50. Obviously 80 is not equal to 50, so it is not binding. And constraint 3, x2 is greater than or equal to 20, which it is, so it is binding. So shadow price. Shadow price for the ith constraint of an LP is the amount by which the optimal z value is improved if the right hand side of the ith constraint is increased by 1 unit, and this little delta here to represent that. So for the first production constraint, suppose now that 2000 plus delta units of production materials are available. So the optimal solution was found where this production constraint and x2 equal to 20 meet. So solving using simultaneous equations again, solving for x1 and x2, doing the same thing as before, except we've got a little delta on the end here, come up with a value of x1 is equal to 80 plus delta, subbing that back in to the constraint, we can solve for x2, and x2 comes out to be 20 minus 7 over 20 delta. So using both these values, we can substitute that back into the objective function, and then we arrive with, on the left here, we've got 13,000 plus 100 delta minus 70 delta, which ends up to cleans up to 13,000 plus 30 delta. So what this means is, this is our original optimal solution, which was $13,000. And plus 30 delta, which means that the shadow price for this production constraint is $30, meaning for every 1 unit increase in the production constraint, the optimal z value will increase by $30. For the first demand constraint, it was not binding, so the shadow price is always going to be 0, since the right hand side is not going to change the optimal solution at all. So you can skip that one. But for the second demand constraint for desktop computers, suppose now that the expected demand is 20 plus delta. Do the same thing again, simultaneous equation, except now there's deltas in here on the second equation. And then solving, x1 is equal to 80 minus 8 on 3 delta. And subbing that back in, you see that x2 is equal to 20 plus delta. And so putting that back into our objective function, cleans up to be 13,000 minus 16.67 delta. So the shadow price is actually negative. For every 1 unit increase on the right hand side of the second demand constraint, the optimal z value is actually going to decrease by $16.67. And that's it for my assignment 2. Thank you for listening.